Hi, good afternoon, everyone. So my name is Charlotte Hu, and now I'm a postdoc in Shirley's lab. And today I will give a guest lecture on the topic of long-range Chromatin interactions and regulatory network. So let's start. So today I will cover 4 sections. So the first one is to discuss something about the enhancer-promoter interaction loops. So actually, this is like the basic element of the DNA structure. Then when we like move higher, we need to see like really the 3D structure of the whole genome, like those very long DNA strand, like how it organizes in the nucleus. So I will discuss that. In the third section, there are also like studies want to check what are the dynamics of those 3D structures, right? So below the cell is the efficiency, it changes all the time. Same as those like DNA structures in the nucleus, they also change. So whether those changes are meaningful or useful, we will discuss that. So the last section of this lecture is I will also discussing something about the gene regulatory network. Because of course we will learn many things about the regulation among the DNA and DNA itself. So it's so-called cis regulations. But actually, in reality, most of the really the entry point, like to start the whole like machinery is the regulation by transcription factors. So that's why the whole like gene regulatory network is somehow more important for us to understand the function of cell. I will give some examples like why we need to have this network and how it works. Okay, let's start with the first section. So, so I think probably you have seen these slides from the previous lectures. So, so we know that for example, for the human, we have a human genome which contains like 3 billion ACGTs, right? 3 billion characters. So, but that's not the end of the story. Actually, it's just like the basis of any life phenomena, because they can have like different modifications on DNA. So instead of those ACGT, there are some modifications on the chemical structures, make it either it's like suppressor region or it's like can be read by other proteins. So there are some changes. Not every base are the same. So that's why we somehow need to measure the DNA methylation pattern, and in some cases they are very important for the function of the DNA. So besides DNA methylation, so from this figure, you will see that usually like DNA is walking around on some proteins, and those proteins called histone proteins. So you can see like here. Again, they can be different modifications on the histone proteins, and actually different modifications can really change the function of the DNAs that's associated to it. So for example, like some modification may make the DNA fragment more easily to be recognized by other proteins. Some make it harder. So that's why above of DNA, we also need to learn the nucleosome position and the modifications on those nucleosomes. So the third one is related to this is also called like a Chromatin accessibility. It's somehow related to the histone. So you can imagine if for some reason those histones are densely packed, then there is no way for the other protein to access the genetic information in this region, in the whole DNA region, right? So that's why like sometimes people just define like what's the accessibility of different DNA fragment across the whole gene. And sometimes this can really like change, cause disease or have different phenotype. Then the last part is the focus of what we will discuss today is those like even higher order of Chromatin interactions. So why we call it higher order? Let's show you a lot of figure about this like hierarchy. So again, on the left is the DNA, right? So it's a simple strand. Then we have like those DNA that are walking around on the nucleosome, and then like a different nucleosome have different modification and then have different function. So even above of this, for the DNA, it's like a one-dimension thing, right? It's a strand. However, it's lived in the nucleus. It's a 3-dimension space. So that's why you can imagine that they can like walk around, have interaction with each other, And this kind of interaction is so-called higher order of chromatin interactions. So as the example showing here, you can see there are like three helping loops in the DNA region, right? So for the helping loop, I mean that, so if we just focus two regions, if we see it in the one dimension, they're very far away from each other. But in the three dimension, they're very close. And in real case, that many of those interactions is so-called enhancer promoter interactions. So of course, I will like explain this more in the next slide. But you can imagine that because of those like naturally happening interactions, somehow our like cells try to utilize those like existing patterns, try to like really build up a regulatory like a machine regulatory like a logic, like when sometimes we want to turn on a gene, sometimes we turn off, depending on the structure of the DNA. So of course the DNA structure is very complex. So that's why people also define like a different like an even higher level of description on the structure. For example, like people want to define like so-called topology association domains, the TAD domains. So for the domain, you can imagine it's just like it's a region that there are a lot of interactions within, for the regions within the same domain. Well, for the two regions, that's among the two different domains, there are less interaction. So the domain is really like a space that there are a lot of interaction. So similar to the TAD domain, people also like define this laminar like associated domain, which is similar to the TAD domain. And then on the top level, we also have different chromosomes. So for the human, hope you know that we have like 23 pairs of chromosomes, and each chromosome is a one like very long strand. While in the nucleus, we have like so many strands working around to each other. So the whole structure is very complex. So that's why until very recently, people have found a way to study the 3D genome structure. So before like moving into the how we study structure, let's just give you an example like why we want to study it. Because as I mentioned, like we know there is a gene, right? So the starting point of a gene is so-called a promoter. Like it's the location where the polymers will transcribe the gene into an RNA. So this is called the promoter region. However, the expression, those transcriptions are not always only controlled by the promoter. In many cases, they're also regulated by a larger piece of DNA that's sometimes very far away from the promoter. If we just see in one in the DNA, like in the strand. So that's why there are lots of like in the real case, there are lots of interactions among the enhancer and the promoters. Of course, the promoter is next to the gene, right? That's easy to study. We can like quickly find out the pattern to find the promoter. But the enhancers is very difficult. Like how we define those enhancers, and also like there are not only one enhancer, there are multiple enhancers that potentially can interact with the same promoter. So you can see this regulation is very complex. So just to give you like two examples why this is important. Like for the example on the left, in the normal cell, we have an enhancer, which is like this green piece of DNA fragment and the gene, right? So in the normal case, they are far away from each other. They have low interaction. However, in some disease case, because of like some changes on the DNA, then they become interacting with each other. And this kind of interaction will change the expression pattern of this gene during the whole development process. So that's why you can see the consequence of this kind of newly developed interaction is it will change the linear development. Same thing happened for the cancer. So we know that cancer is just a cell that's grow like uncontrollably, right? So that's why people already know there are some genes that can help the cell to grow. For example, some genes can help cell to do cell division or help it to consume like energy and so on, right? So those genes are so-called oncogenes. Of course, those genes are very important when like it's the embryo to like develop like an animal, right? So it's important at some stage, but when people grow up, usually it's not important. So that's why usually we want to shut it down. However, because of the existence of the enhancers, sometimes those enhancers can interact with those oncogenes. And then those kind of interaction trigger this like cell to grow crazy again, right? So that's why like usually it will cause cancer. Another tricky part of those kind of interaction is the 3 examples I show here. So not only the interaction are important, also like where it impacts are also like have different consequences. So you can see here I show 3 examples. The first one is pancreatic cancer. The second one is like the T-cell lymphoma. The third one is colorectal cancer. So you can see there are 3 different cancer types. The cause of those 3 different cancer types, of course, there are many different reasons. However, for the 3 cases I show here, you can see in the pancreatic cancer, there is an enhancer or super enhancer that's at the downstream of this like MYC gene, which is the oncogene in this case. They become like together in the 3D space. Then it triggers the cell growth and become a cancer. Well, in the T-cell lymphoma or in colorectal cancer, actually it's a different region, different enhancer in the human genome that activate the MYC and then have different consequences. So that's why you can see in order for us to really understand why we have those different like limbo development disease or why we got cancer, we really need to understand where are those enhancers and how those enhancers regulate the oncogenes. Then how we can do this? So of course, the first thing is we need to define the enhancer regions. So for the gene, I think it's very easy, right? Because usually gene will be transcribed into RNA. So after we sequence the RNA, then we just map back. We know where are the genes. Well, for enhancer, it's a little tricky because usually it's a small region, and some enhancer they have RNA, but it's not that strong. But still, like this is something. This was a very difficult problem to resolve. So actually, people are already like trying to using some experimental methods to define what are the potential enhancer regions across the whole genome. And very surprisingly, you can see like roughly 13% of the human genome, some region have enhancer function. So of course, not all the enhancers are activated in every case, but sometimes it have function, sometimes it don't. So that's why even the percentage is high, but for each specific cell, actually we don't have so many enhancers. That's function, right? Now after we define the gene, we have enhancer, then the problem is how we can study their interactions. So before coming to the method for studying interaction, let's just give you another example, like why this interaction is very complex. So probably you know that for the human DNA, there are like 3 billion characters, right? So if we stretch this like a human DNA in a string, it's like 2 meters long. As a comparison, so because our cell is very small, if we imagine that our cell is at the size of a basketball, then this whole DNA, this whole string, whole wire will be like roughly 44 miles long. So now the problem is really like you have like this wire which have 44 miles long, and you want to fill it into a basketball. Then what's the structure it will look like, right? So you can imagine it's very complex. There are lots of walking around and action in the middle. Right? So maybe something like what this figure I'm showing is really a mess. Help. But still, we want to learn what's the interaction pattern, because in many cases, those interactions are associated to the enhancer and promoter, and it may relate to some disease. Okay. Then how we can do this? How we study the structure? So only recently, I think it's maybe 5 years ago, people find a way to really study the interaction on the whole genome scale. And the experiment for study this is called the HiC experiment. So the idea of HiC actually is not that hard. The first key concept for designing this experiment is people already know that there are many restricting enzymes. So restricting enzyme is a special protein which can recognize a motif on the DNA. And wherever it recognizes the motif, it will cut it into two. Now, like the example shown here, like the Hino3 is an enzyme. So this it said that this enzyme will help us to fragment the whole genome into small pieces. Right? Then we can start studying. It can be easier to be studied. So a lot of key point of this experiment is if two DNA fragments they are close in the 3D space, then there's a way that they can cross-link the two DNA together, like what's showing here. So if we fix the two DNA fragments together, then because these two DNA fragments, they are cut by the same restriction enzyme. So they are like a flanking region are the same. They share the same like flanking region. So that's why it's very easy for these two DNA fragments to glue together, to ligate it to each other. So that's why, just by chance, we will see many cases that one piece coming from one region in the genome, the other piece is coming from the other region. And if we see it originally like it's like two DNA, they are far away from each other and then come close to each other. Now we have like this hybrid case. In one DNA, half of them coming from one location, half of them coming from the other location. Then the problem is just like we can sequence more and more of those like hybrid reads. Then we know what the interactions look like. So, of course, people designed the experiment, and then the data, the output from this experiment is just to tell you that how many like interactions we can find for each two regions on the human genome. So that's why people are using this heat map to like give an overview of the interaction pattern. So of course, the human genome is very like long. So here I just like usually using people using different bits to draw the figure. So that's why the resolution is a very important issue whenever we draw the figure. Just by looking at this figure, probably we can already get to like a very important conclusion and like understanding of the interaction. So I think the first obvious pattern we can see from this figure is you can see there are clear like different blocks at the diagonal. Right? So if we map those blocks back to the human genome, we will find that like actually the first block is corresponding to the first chromosome. The second block coming to the second chromosome. So the existence of those blocks is really saying that there are more interactions if the two regions are on the same chromosome. Right? So I think this somehow makes sense because if they are on the same chromosome, then they have like a physical constraint, right? They cannot like move very far away from each other. So of course they have higher chance to interact with each other in the 3D space. Another pattern we can see that if we just like look deeper on the diagonal pattern, you can see if the two locations they are close to each other on the chromosome, on the same chromosome, then usually we can see more interactions for these two regions. Right? So I think this is also like something expected because like if we imagine this is DNA, right? So if two regions they are this far away from each other, then if we fix this region, the other region they can move around. Right? It's like a ball. There are lots of opportunity to move around. If they are close, then it's a smaller ball. So they have a higher chance to hit each other in the 3D space. So I think both of these are like somehow expected to see. Another issue, like before we really like check data, is something like what we want to see from the data. So because this kind of experiment, when it was first like designed, it's really difficult to do. So that's why the data we get out of this experiment is not the interaction from a single cell. Actually, it's the average interaction from like tens of millions of cells. Right? Because if you do the single cell HiC, they are possible of doing this, but you have so few material, you cannot see the global picture. It's so difficult to do. So that's why for the HiC data, usually the heat map I just showed in the previous slides is an aggregation of the structure information for more than 10 million of cells. So if there are so many cells, then we can think there are two cases. One case as I'm showing here, is we have location A. It can interact with many other regions. So for example, sometimes it interacts with 3, with 1, with 2, and so on, right? So it's like just open. They can interact with many other places. Another case is another region B. It always interacts to the same region on the human genome, just like the promoter enhancer. Maybe this is a very important promoter and enhancer interaction, so it's always connected. So if we just assume that there are only 5 cells and they have these 2 kinds of interaction pattern, and then you can see for each cell the interaction are actually different, right? After we aggregate all those interactions and then check the overall picture, we have a heat map looks like this. Right? So the first, the location A have 1 interaction with 1, 2, 3, 4, 5, and the location B have 5 interaction with location 6, something like this. Then you may notice that we somehow can assume that if we sum up each location, they should always have the same number of interaction to other places, no matter whether it's scenario A or scenario B, right? So that's why after other people did the experiment, because experiment no experiment is perfect, so there are always some randomly some noise. So the data we want to get from this kind of experiment is actually each location they have equal feasibility, meaning that if we sum up the locations starting from each location, they should be a constant number. They should be the same number. Like in this case, if we sum up all the locations starting from A, then it's 5. If we sum up all the interactions starting from B, it's also 5. So this is somehow the data we want to see. But in reality, it will never be the case. Then how we can resolve the issue? So actually, there are a standard way of doing this, which is this Knopp algorithm. So the way to perform this algorithm is very simple. Of course, behind this procedure, there's some mathematical proof, which we won't discuss in detail here. But I think I can show you the idea, how people can somehow correct the data, the experimental data, and let it to follow the assumption we just discussed in the last slide. So for example, if some people do the experiment and we have 3 regions, right? 1, 2, 3. So it's a 3 by 3 matrix. Then for the matrix A, you can see for this A, it just say that we observe 8 interactions starting from the first location and end to the first location. So it's 8 interactions. Then the 4 meaning that we have 4 interactions starting from first location and then end to the second location. Now, if we sum up each column in this matrix, you will notice that they are not equal. For example, the first column, 8 plus 4 is 12, right? The second one is 4 plus 2 is 6. The third one is 0, 0, 9, so it's 9. So the total sum of each column now is 12, 6, and 9. They are different. Why is different? It can be due to different reasons. For example, maybe the first location, they have some sequence pattern that's easy to be sequenced by the sequencing machine or by during the PCR application or anything. Right? There are lots of experimental bias during this process. So that's why no matter what the structure looks like, we always see lots of interactions coming from location A. For the second location, maybe it's a reverse. Those regions are very difficult to sequence. There are lots of GNCs, so there are some special structures in the PCR design. So that's why no matter what we do, we always get less data for the second location. Okay, so if the data is like this, then how we can somehow reduce the bias in the data? So the way to reduce the bias is somehow straightforward. The first thing is we want to know what's the bias of each location. So what's the bias of each location? Actually, the bias is just the total sum of each location, right? So because as we discussed, the first location we see lots of interactions, then they just have more bias on the first location. So of course, for the purpose of calculation, we can somehow normalize the bias make it easy to compute. For example, the first location is 12, right? So if we divide 12 by 3, then it's 4. And the second location is 6, then 6 divided by 3 is 2. And the last location is 9, then 9 divided by 3 is 3. So this 4 to 3 is somehow the bias. So of course, the reason I divided it is just like help us to do the computation. You can divide it or you don't divide it. There are different ways of doing this, but the process is the same. So after we load the bias, which location, then how about we just divide the number of interaction we see in the data by the bias we get from the original matrix. So in this case, like you can see, we observe 8 interactions from location A, from the first location to the second to the first location, right? So then it's just divided by 4 and 4, because the bias for the first case is 4, the other is 4. The second case for the 4 is meaning the interaction from the first location to the second location, right? Now, the bias for the first location is 4. The bias for the second location is 2. So that's why the formula is 4 divided by 2 times 4 times 2. Right. So after we do like this, like some kind of normalization, then we have a new matrix, and suddenly you can see that the new matrix become really like a balanced matrix. So if we sum up each column, they become to be 1. So of course, you may wonder like whether it's always like this. So of course, it's not always like this. But the example I gave here is a special example that we can correct the bias in 1 iteration. In the real case, maybe sometimes we need to run this like procedure for multiple iterations. Then the bias will like gradually reduce until they become like so similar to each other for all the locations. So of course, there's some like a mathematical proof like it will converge if we just repeat it again and again and again. Okay. So this is the end of the first section. So you guys have any questions on like the structure or this algorithm? Okay. Yeah. Okay. Let's restart it.